So I'm sitting in front of an ICP optical emission spectrometer. And like many modern instruments, everything is encased in plastic because they want the internal workings of the instrument to be protected from changes in temperature and other things that might happen in a lab environment. And that in this particular instrument really limits our ability to see inside and see all the elements we've talked about. So what I'm going to do is show you what's inside the instrument, and so you understand that there are components of this that sort of map onto what we've been talking about in lecture. So, shown here is a diagram of what's inside the OES. And as you can see, it's a pretty complicated instrument. It has everything from sample handling, that actually you have to take a liquid sample and turn it into gas. That then goes through a plasma. You're actually making a 10,000 degrees Celsius plasma in order to ionize the atoms. And when those atoms get ionized, they emit light. And that's what we're detecting in the final spectroscopy of this system. So if you want to detect, let's say, sodium, you're going to park the wavelength of observation at a different wavelength than if you're going to study, for example, chromium. And that's how atomic emission spectroscopy can be so selective. And we detect how much is there by how intense the light is coming out of it. So one of the most important things to analyze for in any sample is going to be the metals. What metals are in the sample and how much are there? So the instruments we're learning about for metals analysis are really basically all atomic spectroscopies. There's methodologies that let us measure what atoms are in a sample. And this instrument, the atomic emission spectrometer, accomplishes that goal by looking at the atomic emission from the sample. So what you see here is actually starting off, you put your sample, there's actually a little plastic tube that sucks in the sample continuously. And this is a nebulizer that goes from the liquid state to a gas state, because the only way you can actually see an atom from atomic emission is if you turn it into a gas. And what's really cool is that sample then goes inside this machine, and this bright image here is actually a plasma. That plasma is made with argon gas, and it can reach temperatures as high as 10,000 degrees Celsius. What that's going to do is atomize everything. It's going to put them into highly excited states, all of these atoms, and all the liquid's going to go away. And those atoms are going to eventually drop back down to what's called their ground state and emit light. And that light is going to be a different wavelength depending on the atom. So over here, for example, we tuned the spectrometer inside the OES to look only at 267 nanometers. And that's one of the characteristic fingerprint wavelengths of chromium. Only chromium will emit there. So if you have other atoms that say iron or copper in your sample, you won't be detecting them if you only look at that color. And you'll notice in this graph and in this graph, we're using some other wavelengths for chromium emission. And then what you see here is one of the most important features of any metals analysis, and that's the calibration of the instrument. Instruments usually give you a signal, but they don't tell you what that signal means. They don't translate it for you. So to translate it, we take a series of samples that are of different dilutions, a really dilute sample and a really concentrated sample, and we measure how big a signal do we get when we know exactly the amount of chromium we're putting into the instrument. And by changing that over a large range, we effectively translate the instrument signal into the chromium concentration. That's called a process of calibration, and it's a really fundamental thing you do in analytical chemistry, particularly in metals detection. So the OES spectrometer is a real go-to system. You use it for a lot of samples. You can't use it for solids, of course. They have to be in a liquid phase. They have to be able to be sucked up through that straw. But pretty much almost anything you can imagine that's liquid, that has a metal in it, you can analyze using this machine. Typical detection limits are going to be on the order of maybe 100 parts per billion, possibly a little bit better depending on the configuration of the system.